For we are opposed around the world by a monolithic and ruthless conspiracy that relies primarily on covert means.
Connecting the Dots with Dan Happel. Tonight's featured show is Connecting the Dots with Dan Happel. Welcome to the Republic News Network for our live national broadcast. You may call me Kelby, and tonight I'm going to be acting as your moderator. The RNN, which stands for the Republic News Network, has been doing this radio show since 2010, and it's always been a friendly introduction for the people of the United States Corporation. Here we go. It's true. The United States is a federal corporation, and their exclusive jurisdiction is in the District of Columbia. The Republic government was simply a bunch of U.S. citizens that in law don't have access to the Bill of Rights, and they realized they wanted to be Americans as our founders and our law provided each and every one of us. See, we've been hard at work since 2008, and since 2010, we have successfully re-inhabited the original government vacated under Lincoln in 1861. I know, it's hard to understand. Don't worry. We are law-abiding, peaceful Americans and very pro-government, and we love our country. You can consider the Republic members are tired of the corruption that we see every day. See, we found in the law that there is two forms of government here on the land, and we did something about it. We are people. Mothers, fathers, sons, daughters. We have families just like you. We simply found some truths, and now we're sharing these important truths with the rest of the world. So get ready to hear things that sound amazing, and get ready to understand that you too are about to be a part of history. We welcome each one of you to Connecting the Dots with Dan Happel and your Republic if you so choose. But before we go into our broadcast tonight, please bow your head in prayer. Father God, we want to thank you so much for this opportunity to just listen to truth from these scientists, these men that are just going to expound really what's going on in this world. So, Lord, bless and protect them and keep this mission going of telling the truth to the people. And we pray this in your Son's name. Amen. Ladies and gentlemen, without further ado, Mr. Dan Happel, I yield.
All right, Kelby, thank you for the introduction, and I welcome our listeners to another program in Connecting the Dots with Dan Happel. Tonight we have a really interesting couple of folks that are going to be talking about a new scientific theory that they're convinced will completely challenge the existing greenhouse theory. And I think their backgrounds and their scientific basis is certainly fairly straightforward and logical, and it makes a lot of sense. And at the very least, I think the scientific community should wake up and pay attention to our guests, Dr. Ned Nikolov and Dr. Carl Zeller, and they are both very active in the scientific background and forestry and so forth. Dr. Nikolov is involved with forestry with the U.S. Department of Agriculture. However, I have to say his scientific work on this theory was done completely outside of his normal work time with USDA. So this is an effort on his part to try to clarify some things that are troublesome if they're not really explained in a very sound way, and things that really challenge a lot of the traditional, let's say conventional thinking on the greenhouse effect of various so-called greenhouse gases. So with that said, I will first introduce Dr. Ned Nikolov. And Dr. Nikolov, would you give our listeners a bit of a background on you and what your experience is in scientific efforts?
Thank you, Dan. I really appreciate this opportunity. I think your audience will be pleased to hear something new that have not been in the public domain before in terms of science and new insights. In terms of my background, I have a bachelor and master's degree in forestry from the Forestry Institute in Bulgaria. I came from Bulgaria in 1991 as the visiting scientist here to the United States. And I was invited by the U.S. Forest Service, and at that time, Dr. Zeller was the a researcher at the Forest Service, and he actually was instrumental to invite me to come to this country. And I came here, I started my research, my work, then I involved in a graduate study with the Colorado State University, and in 1997 I obtained a PhD degree in ecosystem modeling, ecological modeling, that involved exchanges of energy and trace gases between the ecosystems, surface ecosystems, and the atmosphere. I then completed a postdoc of about 4 years at Oak Ridge National Laboratory, where I work in a unit that was involved in global research related in part to climate change, in part to carbon sequestration. And from 2001, I came back to Fort Collins, Colorado, where I originally arrived in '91, and I started working in air quality. And then I joined a project that Dr. Zeller had, which had to do with the prediction of the forecasting of fire weather. Those are a weather forecast specifically tailored to help the management of forest fires. And I've been in this project. I was originally as a postdoc, and then I was a contractor until 2010, and then there was an opening for a manager of this project, and I was accepted the position, and then since 2010 until the present, I've been working for the U.S. Forest Service as a manager of this project. The name of the project is Rocky Mountain Center for Fire Weather Intelligence. So that's in brief, in short, and my expertise, I have done work in different areas. I started with ecosystem modeling and ecosystem processes, the nitty-gritty of the exchange of carbon dioxide, water vapor, and heat between ecosystems and the atmosphere. I have done work in remote sensing, retrieving some vegetation characteristics like leaf area index from satellite images. And over the last 15 years, I specialized in developing applications to help the firefighters combat the forest fires, and also help them assess the fire danger based on weather forecasts. And as of 2012, 11, I would say, I got involved. This was on my own, out of curiosity in the climate research, and the way my interest started was because of ClimateGate. When those emails came out in 2009, I started reading about the correspondence that was placed on the web. And what I found, I was a very firm believer in the conventional greenhouse theory and everything as advertised. In fact, I used to argue with some of my colleagues that had some doubts. They were not scientists, but we had some heated arguments, and I would tell them that they're insane to think that thousands of scientists would be wrong, and that the IPCC, Intergovernmental Panel on Climate Change, reports would be wrong. And I was a very, strong defender of that. And then the ClimateGate emails came out, and I saw that there was an obvious attempt to hide information. They were not forthcoming, and I got curious about the discrepancies that I started to realize at that time. I didn't know a lot about those at that time, 2010, but I started researching them because I was curious about the science, the physics. I didn't care so much about the politics, because politics is a subjective matter, and you could not really resolve the physical issues with politics. But I focused on the science, and the more I was studying, it took me about 8 months intense readings of scientific literature. I found more and more discrepancies, and then I thought to myself, this theory is not holding up to the evidence, and so therefore there has to be an explanation, there has to be an alternative explanation. So I started looking for alternative explanation, then we stumbled on the research that we'll be discussing later on in this talk. That's in short.
Okay, well, great. That certainly should give our listeners a really good understanding of how complex your background is and how it really does lend credibility to everything that you're going to be telling us tonight. Dr. Carl Zeller is our other guest on the show, and Dr. Zeller, I'd like to give you an opportunity to explain how you got involved in this process, and a little bit more information on your background as well, so that we can let our listeners know that we're talking to a couple of really solid scientists.
Okay, well, I'm kind of a normal guy. As a young man, I was interested in getting off the farm, and my dad told me I had to go to college, so I went to the Virginia Military Institute and studied civil engineering. But then when I joined the Air Force, I found out that civil engineers, all they did was fix parking lots and air conditioners, and kind of boring, and I was adamant about being in the Air Force and not the Army, so I became a weatherman in the Air Force, and that's where I went to school and learned how to forecast the weather. Basically, I've been in weather, getting out of the Air Force. I did stay in the Air Force as a reservist, but getting out of active duty, I went into air pollution, and my young formative years in the science of meteorology was both weather forecasting and in air pollution. I worked for many government agencies. I worked for many private companies as a consultant. Through the years, I have worked for the EPA and for the BLM, and for recently, before I retired, for the Forest Service. While at the Forest Service, I did get my advanced degrees. Both Dr. Nikolov and myself are here in the Fort Collins area, Colorado State University. So I did get my advanced degree at Colorado State in fluid mechanics with an emphasis on micrometeorology. So this is kind of funny. Here we are talking about macro climate, and I did a lot of my work in micrometeorology. But that micrometeorology is what led me to find Ned in Bulgaria. He was working on a model, if you can believe it or not, of a tree, and he had a mathematical model of a tree or a canopy, and how it would breathe, and how it would actually take in carbon dioxide and spit out water vapor. And I thought, man, we need this guy over here in the U.S. And that's how Dr. Nikolov and I got acquainted, and how we got started. When he came over here, we did actually finish his model, and we integrated it into a mesoscale weather forecasting model. At that time, it was called MM5. Now it's called WRF, and his tree model, which actually puts up water vapor, that sort of thing, improved our temperature and our water vapor or relative humidity forecasts. That's about it. Okay.
Well, that's good, and I have to tell you, gentlemen, that's an interest of mine too, is forestry. I am with the Montana Forest Stewardship Foundation, and I am chairman of the steering committee. I've been involved with the stewardship program in Montana forestry for almost 20 years, and it's an area that is near and dear to me, and it's a tragedy what's been happening in our state, as you're well aware of, with all the fires, and the lack of good management that we've had on our force as a result of some really stupid federal policies that are, at least in part, due to some of the modeling that you gentlemen are going to prove that traditional greenhouse gas theory is not very accurate. So, let's start out with a discussion of what the greenhouse affect the current greenhouse theory, and I would like to do that question first, so that it can give our listeners a background on some of the fundamental assumptions and premises of the current greenhouse gas theory.
So I guess I can answer this question. The current greenhouse theory, basically, it emphasizes the greenhouse gases, and the core of the theory is that solar radiation comes from the sun, of course, and it warms the Earth's surface. As the temperature of the Earth's surface rises to a certain level, or any temperature above the absolute zero, it causes an object to emit long-wave radiation. This long-wave radiation is different from the short-wave that comes from the sun, and the difference is in the wavelength of the photons. The long-wave radiation goes out to space, but it gets intercepted by certain gases that have a high absorptivity to specifically long-wave radiation. Those gases are nearly transparent to short-wave radiation, but they are absorptive. They have high absorptivity to long-wave radiation, and those gases are carbon dioxide, water vapor, methane, some of the nitrous oxides, ozone, but the two primary ones are carbon dioxide and water vapor. In fact, water vapor has a stronger absorptive capability than CO2 by far. So then those gases, because they absorb, they have high absorptivity, they also have a high emissivity to long-wave radiation. So the second they absorb radiation from the surface, they also emit it. And they emit radiation in both directions, to space and towards the surface. So the radiation that gets emitted towards the surface gives rise to a long-wave radiative flux that's coming from the atmosphere down to the surface. It's measured. And in fact, there is a global average value for this flux, and it's about 343 watts, 343 to 346 watts per square meter. This is a global average. It does vary with latitude. The flux is higher in the tropics and much less in the polar regions, and that's because the flux is a function of the temperature of the air. So when the air gets colder, the flux gets lower, but it is also a function of the amount of water vapor and CO2 in the atmosphere.
Yeah,
so we should say that flux is an amount of energy per area per time. Yeah, basically it's a power per unit area. Power per unit area.
Okay.
Okay. So the current theory sees or understands this long-wave flux that is measured coming down towards the surface as the reason for or the mechanism through which the atmosphere warms the surface. It is called a greenhouse effect because the analogy is made with actual glass greenhouses that are warmer, but the current science also understands that the actual greenhouses do not work as the atmosphere because the greenhouses, they preserve heat by obstructing the mixing of air from the inside with the outside air, or this is called convection. They're preventing the convective heat exchange between the inside and the outside because they have a glass roof or glass walls. And this is the reason why the air being trapped inside, physically trapped, it increases its temperature. In the atmosphere, we have no trapping. We don't have any walls. We don't have any roof. So they say that what plays the role of the greenhouse in the atmosphere is the back radiation, this long-wave flux of radiations coming down from the atmosphere, which has the value of about 343 watts per square meter. And they say that this is the reason why the atmosphere provides the thermal effect to the surface. So therefore, according to the standard theory, if you change the concentration of some of those gases like CO2 in the atmosphere, carbon dioxide in the atmosphere, you will change the emissivity of the atmosphere. Therefore, there will be more. So if you increase the concentration, the emissivity of the atmosphere will increase as well, which will cause a higher flux of long-wave radiation to come down, which will cause warming. That's the standard theory. So that's why the greenhouse theory is called also radiative greenhouse theory, because it is based entirely on the notion that it is the concentration of those gases in the atmosphere that create opacity to the atmosphere. This is opacity with respect to long-wave radiation. In fact, the technical term for that is optical depth. So by increasing the optical depth of the atmosphere to long-wave radiation, warming occurs on the surface. That is what the current theory says. There is, however, one interesting fact, which is based on observation, and that fact is that according to the theory, if you read an explanation of the greenhouse theory in a textbook or a popular source like that, you will see something like this, that the shortwave radiation from the sun is the ultimate source of energy. So the shortwave radiation comes to the Earth, gets absorbed by the Earth, or part of the radiation gets absorbed. There is a part that gets reflected straight to space. It's called albedo, because clouds reflect the sunlight. There's also the surface reflects a certain amount of sunlight. But the radiation that gets absorbed hits the surface, and then long-wave radiation comes out. It gets absorbed by the greenhouse gases, and part of it gets directed downwards, part of it goes out to space. Now, listening to this description or reading this description, you would immediately, if I were to ask the question, what do you think is the size or the magnitude of the long-wave radiation coming down compared to the size of the total flux of short-wave radiation absorbed from the sun? People immediately will say, well, it has to be less or equal than the radiation coming from the sun. Why? Because this long-wave radiation is supposed to be a product. It's like a transformation of short radiation that was absorbed by the Earth. It's not a separate source of energy, right? Well, the observations show something very interesting. The total amount of short-wave radiation absorbed by the planet and the atmosphere, the entire system of Earth together, is about 240 watts per square meter. At the same time, the observed flux of long-wave radiation coming from the lower atmosphere towards the surface, it's 346 watts. So we have about 43% more radiation coming from the atmosphere down in form of long-wave flux compared to everything that we receive from the sun. How this is possible if the greenhouse effect has to be a result of pure transformation of solar radiation from shortwave to longwave? So this observational fact that the longwave flux is much higher than the total absorbed from the sun, it tells you that there is a different mechanism that has to be responsible for the heating of the surface, and that maybe the long-wave radiation that we're observing is a result of this different mechanism. It's not the cause for the warming, but it's actually a result of it. So this is one of the questions that we have addressed with our research, and we tried to find the answer, and we think we found the answer to that. Incidentally, talking about this comparison of long-wave to short-wave fluxes, if you look at the case of Venus, Venus has a very thick atmosphere, and it's a very hot planet. The temperature on the surface is in the order of 463 Celsius or 737 Kelvin, compared to the Earth, where the temperature on the surface of the Earth is about 14 degrees Celsius or 287.4 degree Kelvin. So Venus is much, much hotter. The long-wave flux that is measured on Venus coming from the lower parts of the atmosphere towards the surface is in the order of about 16,000 watts per square meter. At the same time, Venus, because it has a very thick cloud cover and it reflects a lot of radiation back to space, it absorbs from the sun only about 65 watts per square meter. So you have 65 watts per square meter absorbed, being converted into about 16,000 watts per square meter down on the surface. Something, if you try to explain this with just a transformation of solar energy from shortwave to longwave as the greenhouse theory attempts, it doesn't add up. This kind of explanation, it violates the law of the first law of thermodynamics, which is the conservation of energy, but it implies that that nature has some other mechanism. So this mechanism of trying to explain the thermal effect of the atmosphere has to be wrong, because this mechanism leads to direct violation of the energy conservation law, and you could not have that because nature does not violate its own laws.
Okay,
That's
good.
Sure.
Good. Dr. Zeller, do you have something to add to this?
Well, what I was going to say is that what the current standard climate scientists would say is, well, of course, Venus has 96% carbon dioxide, and we predicted that, right? They predicted that that atmosphere would in fact store that energy, but that's not what Dr. Nikolov is talking about. We're talking about the actual. If you look at the energy in and the energy out, this business of storing, the thermodynamics does not back that up.
Well, the other thing I wanted to point out that the key assumption in the current greenhouse theory is that a free convective atmosphere can trap radiant heat. This notion of trapping of radiant heat, it comes from the 19th century, and it was first proposed by Joseph Fourier, who was a French scientist and mathematician. We use some of his methods today in mathematics. He was a brilliant mathematician, but he didn't have much knowledge about the physics, and they had limited data anyways back in those days because this was 1827. He proposed the idea that maybe the atmosphere works like a blanket that preserves the heat. And this idea of blanketing, effect of the atmosphere went on for several decades. And in the middle of the 19th century, another scientist by the name of John Tyndall, he did the first experiments with infrared radiation. He found that certain gases, specifically CO2, carbon dioxide, and water vapor, were indeed capable of absorbing more infrared radiation than other gases like nitrogen or oxygen. And to him, it was bingo. Yes, if those gases absorb more radiation, that means they can trap it. So there was immediately the equating of the absorption of more radiation, long-wave radiation, with the actual trapping of heat in the atmosphere. And this connection is alive until to this day. And when you express, and I have said this to many people online and also in private conversation, when I say, where is the evidence that the atmosphere can trap heat? They say, well, this has been known, has been measured, for over 100 years. The absorption of higher absorption of long-wave radiation by certain gases is a fact. Yes, it's a fact, but it doesn't mean that higher absorption does not imply trapping of heat, because in order to trap heat within a gas, we know this from practical experience, it requires an enclosure. It requires that the mass of the gas is actually restricted, prevented from exchanging heat with the surrounding environment. In a free atmosphere, you have not only radiative transfer as a mechanism to exchange heat, you have also the heat also gets exchanged by fluid motion. It's called convection. And the convective heat exchange is many orders of magnitude more effective than radiation because of a number of mathematical reasons that we probably don't have to discuss here, but it's many orders of magnitude. One order is like 10 times. So we're talking about many orders, like 60, 70, 100 times more effective in transporting heat than the radiative transfer. And when you have this mechanism present, it overrides the radiative transfer in a way. So the bottom line is that free convective atmosphere cannot, in principle, trap heat. It requires a lid on top of the atmosphere in order to trap the heat, and we don't have such a lid. So that's where the core of the greenhouse effect of the current greenhouse theory is, which is the heat trapping effect of the atmosphere.
Yeah. So there's the two things is that the absorptivity of any molecule is exactly equal to its emissivity, and it's immediate. It absorbs it, it immediately emits it. And then the climate models, when they run the climate models, they have this excess in the model itself, so-called trapped heat above the tropics, in the air above the surface, and that has never been measured. So that's that's kind of a.
Sorry, Dan, I got to take a brief intermission, and we'll continue with the Dan Happel Show. A story of a common family. So my daughter asked me a very important question. She said, "Dad, why do you work so hard on this republic?" And I answered her, "Well, baby, the republic as given by our founding fathers is the most important form of government ever given to man." She said, "Dad, why don't you let somebody else do it?" I said, "Well, sweetheart, most of America thinks things are okay. And so long as their lives are not upset, they don't have to care about the important things that are taking place in their own country. Your dad likes to do things. I just don't want to sit and wait for somebody else. And if we didn't have our founding fathers, we wouldn't have this country. They were doers. They wanted something great for their children and grandchildren. And sweetheart, so do I." Ladies and gentlemen, I wish I could say that that's what happens in almost every home of our country, but it's not. Just 8 years ago, as a man who watched an $800 billion bailout given to banks when that money could have paid off every home in foreclosure in this country, which would have resulted in the banks getting the money anyway, I realized that we had a problem. And I stood up and I did something about it. I'm asking you to do something about it. I'm asking you to not just listen to these phone calls. I'm asking you to go to republicfortheunitedstates.org and read the Declaration of Sovereign Intent. Understand what we have done over the last 8 years. Understand what our intention is, what we are desiring to do for the people of this nation. And do something about it. Participate in the phone calls. Participate in building your states. Participate in finding a governor, finding a leader, finding the body politic of people that are going to stand up and build the de jure state. This is what we need. We need you to do something about it. We need you to be doers. Wednesday night of every week, we have a Building the States phone call at 6 p.m. Pacific. We encourage you to get on this phone call and understand how you too can be a doer. Thank you. I yield.
Kind of a indication that there's something wrong with those models.
Right. Yeah. So Dr. Zeller is talking about a key prediction of the climate models that use this trapping effect, which is purely theoretical. As I said, it's never been shown experimentally that a free gas can trap heat. Because if that were the case, you would have engineers would use carbon dioxide and water vapor to do radiation insulation on your houses. But it doesn't work because they know very well that those materials do not trap heat. But anyway, so one of the key predictions is that over the climate models, that in the middle part of the troposphere, over the tropics, they predict the highest rate of warming as a result of increasing concentration of carbon dioxide. It's called the hotspot, and this hotspot has not been measured in reality, which immediately says and shows that something is inherently wrong, fundamentally wrong with the entire theory.
Well, as a matter of fact, I've seen some of the scientific reports where they've tried to show where the areas of greatest increase in temperature, assuming that the equator is going to be the highest, and it isn't. It ends up being up in other areas, which leads one to understand that the actual temperature models that they're using are not accurate. They're just not working according to their own science. Could I, first of all, we know that CO2 is supposedly the culprit that's causing the biggest amount of angst to some of the IPCC and some of the people like Al Gore and folks who are saying that man-caused global warming is a result of increases in CO2 in our atmosphere. But according to all the science that I've seen, CO2 only makes up 0.4% of the entire atmosphere. And frankly, I think water vapor has a greater capacity to trap heat than CO2. How could they claim that such a small percentage of gas has the ability to increase the temperatures that much?
The answer to this question is kind of lengthy, but I'll try to make it real short. So they divide the gases in condensing greenhouse gases and non-condensing greenhouse gases. So water vapor is a condensing gas, which means it gets evaporated from the surface. It condensates at some height and comes down as a snow or rainfall, and therefore it doesn't stay in the atmosphere for a long time. When the carbon dioxide, they say it stays in the atmosphere for a long time. In fact, some of their models predict like hundreds of years. But then if you go back, like in the 50s and 60s, where a lot of research has been done with radioisotopes of CO2, and they have found that the residency time of CO2 in the atmosphere is in the order of 10 years, maybe between 7 and 12 years. So, but this research has been basically ignored, and then some models were introduced, and now the conventional wisdom is, and what you see in most of the textbooks, is that they're talking about the CO2 that's being emitted now will affect the climate after 150 years, because the residency time of the CO2 in the atmosphere is very, very long, which was not supported by the empirical data before. But this is besides the point. The entire notion that changes of composition of the atmosphere can affect climate resides on the fundamentals of how we understand the greenhouse effect, how it works. I described a little bit, just a few minutes ago, what the conventional theory says about the greenhouse effect, and but there are discrepancies in between observations and theory to the point that it makes you question the very fundamentals of that theory. Does the atmosphere really work as a blanket? Does the atmosphere really works by reducing the cooling of the Earth's surface because it has the greenhouse gases, or there's an entirely qualitatively different mechanism that can explain the thermal effect of the atmosphere? We prefer in our papers we don't call it the greenhouse effect because it's a wrong term in our view, and this has been also acknowledged by the mainstream science, because the real atmosphere really has no analogy with the actual a glass greenhouse, right? So we call it a atmospheric thermal effect or atmospheric thermal enhancement, which is the acronym is ATE. That's what we call it, and we believe that this is a much more accurate term for what is now known as a greenhouse effect. So here we come to what the core of our findings are, and maybe we can, and Dr. Nikolov Zeller can go over a little bit the history of that to maybe talk about this, how we got to this, and then I'll talk about the actual discovery.
Okay, that sounds good.
Okay.
Dr. Zeller, it's your lead.
Okay. Well, I wanted to start out by saying we do not call our science a theory. It's actually a discovery. So we made a discovery, and then out of this discovery comes some equations and comes a theory. I did want to say that, basically right now, our discovery and our theory is pretty much not accepted by the scientific community. And when I say scientific community, I mean both the conventional climate scientists and also the skeptics and deniers. Ned and I, Dr. Nikolov and I, do not consider ourselves deniers or skeptics. We consider ourselves scientists. Now, this non-acceptance, I think, is based on folks mixing, because of the carbon dioxide, mixing air pollution with climate change. And there's a genuine fear out there with whenever you talk about climate change or climate warming. Right now, we've got Irma off the coast, threatening Florida, one of the strongest hurricanes we've seen in years. Now, we haven't seen any hurricanes. There's been a dearth of hurricanes for the last decade, and now we have a big, high, Category 5 storm. That generates a lot of fear, and that fear is valid. However, you're going to hear a lot of people saying, aha, that's proof that we're having human-caused climate change. And I think that mixing air pollution with climate change is one of the problems. We need to separate those two phenomena. One of the things what Dr. Nikolov and I did is we started out with asking questions a little bit differently. And as you know, in science, sometimes it's the question that can be asked. If you ask a unique enough question, that will lead to a different answer. And one of the questions that we asked that incidentally resulted in a published paper that took us 4 years to get published, very controversial. And that question was a simple question. What would the average global surface temperature of any rocky planet or moon be? Like, we're talking about Venus or Mars or Earth or Titan. What would the temperature of those celestial bodies be if they didn't have an atmosphere? Seems like a straightforward question. That question has been answered with a very simple calculation called the emission temperature that turns out that does not have any physical sense. It's a number that's not observed. The temperature, that particular temperature for Earth happens to be 5,000 feet, above the surface. For Mars, it happens to be about 200 or 300 feet under the surface of Mars. So we asked the question, and what would the average global temperature of any rocky planet be without an atmosphere? That led to one of the very important pieces of our discovery. The second thing,
if I just intervene here, the reason we asked this question was because the first step was to assess what is the magnitude or the size of the thermal effect of the atmosphere in terms of degrees Celsius. Right now, the current theory says it's about 33 degrees Celsius. So in other words, if you don't have atmosphere or you don't have greenhouse gases, for them it's equal. Not having greenhouse gases and not having atmosphere is the same thing. In other words, they don't even acknowledge the pressure, they don't acknowledge anything else. So we asked the question, what is really the temperature of the surface of the Earth would be without atmosphere, how we can calculate that, because that will give us an answer, what is the thermal effect of our atmosphere? Is it 33 degrees or something else? And we found that it is something else, and actually the thermal effect of the atmosphere is 90 degrees, about 90 degrees Celsius or Kelvin, which is about 2.7 times larger than currently believed. And this by itself has a very strong implications to the current theory. And I'll just say quickly here what the implications are. Another measure of the greenhouse effect, the way it's adopted now by current science, is not is in addition to the temperature difference between atmosphere and no atmosphere, is also the absorption of long-wave radiation between the surface and the top of the atmosphere. And the way this is measured is that to the satellites, they can measure the thermal flux coming from the surface. They subtract from that the thermal flux at the top of the atmosphere, and they get a difference. And they say this difference is actually a measure of the greenhouse effect. And this difference in terms of flux happened to be about 155 watts per square meter. Now, if we have a thermal effect of 33 degrees, as they believe, 155 watts per square meter difference in absorption, they call it absorption of long-wave radiation by the atmosphere, this flux can kind of explain the 33 degrees. But if the actual thermal effect is 90 degrees, which we have proven in a special paper that goes through all the mathematical reasonings and so forth, you have a problem because the 90 degrees cannot be explained by this absorption by the atmosphere of which is in the amount of 155 watts per square meter.
The difference between the bottom and the top.
Yeah.
So well, and obviously then in the absence of any atmosphere on Earth, it would be considerably hotter than what we have with an atmosphere, which is really.
Well, now there is a misconception also. If you in this work, if you actually look at the moon, the average temperature of the moon, which is not something that planetary scientists usually look for, is about 197 degrees Kelvin. That's considerably colder than the average degree on Earth, which is 288 degrees Kelvin. So what you're saying is it turns out that without an atmosphere, it is much colder on the average, and that's one of the more difficult things of our discovery and our theory is we talk about the global average, the global mean temperature of any given celestial body over the long period. It turns out that NASA has been making these measurements over the last 35 years or so. And basically the data that we used the data that was taken over the last 30 years. So now you can look at the moon and you can find out that the average temperature at the equator of the moon might be a little bit more warmer during the sun, during noon on the moon, but basically when we're talking about the overall global average temperatures with the atmospheres are always warmer than the temperature would be without. And as Dr. Nikolov says, we needed to know what the no atmosphere temperature was of any given body. And the climate scientists before we started were using this emission temperature. That emission temperature never really worked out when we started to make some of these calculations. So we looked at that, and we discovered that the calculation was actually not done correctly. Basically, it's more into the technical area, but they were doing an average of a disk, that the energy that came from the sun, and averaging that over the full sphere of a body, whereby what we did is we actually integrated the sun's energy over the entire planet and did our average that way. But
so basically the difference is that the current method that they estimate the temperature without atmosphere assumes that the Earth is a flat disk.
Yeah.
Mm-hmm.
This is the equivalent. So they use a mathematical
and distributes it over it assumes it's a flat disk, but then it distributes it over the entire surface of a body. What we did is we integrated separately, point by point, and this can be done mathematically through integration, and we determined a very different number. And there's a mathematical law called Holder's inequality that tells you that this is going to happen when you're looking at differences between the energy received by the sun is related to the fourth power of the temperature that results from that. So basically,
in short, they used a mathematically wrong formula to calculate the reference temperature, which is used to assess the thermal effect of the atmosphere. The formula has been used for over 40 years, is mathematically wrong because it refers, not that the actual law behind that is wrong, but the mathematical, the formula is wrong because it refers to the temperature of a flat disk, not the average temperature of a sphere. And that's the main difference. And when we did the correct calculations through the correct integration, we found a temperature formula that produces much lower temperature, which, by the way, our formula was verified against the measurements of NASA and models of NASA. And we have this reference in our paper, in the first paper. So the long story short,
basically it's verified with that NASA measurements of our moon with the Diviner satellite. So basically, it is kind of a proven number. Now, this number, the no atmosphere temperature of a planet or a moon, of course, is going to vary with the distance from the sun. That value, as we're continue talking here, that becomes the key ingredient for our discovery. This is the ability to assess or calculate the no atmosphere temperature of any celestial body.
Okay.
So that was the first question.
I'm going to interrupt here because I'm afraid we're going to run out of time. We're getting pretty far down into the weeds on the science of this, but what I want to do is have you gentlemen tell us in a nutshell what your theory entails.
Okay, let me say real quick. We did ask two other questions, and the second question was, might not the same physical principles that give us our temperature here on Earth be the same for other planets? In other words,
absolutely.
Is there not a cosmic physical continuum? This is a non-question for most traditional climate scientists. Why would you even ask that question? Mm-hmm. Obviously, Earth is the same, and so this is a question that would typically not be asked. And the last question was, well, what would those universal controllers of the equilibrium temperature on any planet be? What are those? Okay, so those are the three questions that we asked.
Okay. And so we started on those questions, and we assume that there is a continuum, and this continuum is driven by some forces that are the same forces determining temperatures on all these different planets in the solar system. But really, our conversation our question started with how we can explain the 90-degree thermal effect on Earth's atmosphere, because the current theory cannot explain that. The fluxes do not match. There is no way you can explain this through the absorption of long-wave radiation by the atmosphere, the 155 watts per square meter that I mentioned. So we decided to look across the solar system and to find what kind of continuum of forces can explain the temperature on Earth and other planets and moons in the solar system. So we looked for data, reliable data, accurate data that are measured over a long period of time, preferably from direct observations for different planets and moons, and we identified 6 bodies, planetary bodies that were meeting our stringent criteria about data quality, and those were Venus, in the order of distance from the Sun. Venus, of course, Earth, Moon is at the same distance; it's our satellite. Mars, Titan, which is a satellite of Saturn, and Triton, which is a satellite of Neptune. So we collected the data through exhaustive search of the literature in terms of the atmospheric composition of different bodies, in terms of distance, of course, from the Sun, solar radiation reaching the bodies, surface temperatures of the bodies, overall total pressure, atmospheric pressure of those bodies, and so forth. So we did analysis of this data using an objective technique called dimensional analysis, which is a standard in physical sciences. And this is a technique specifically designed to infer empirical or physically meaningful relationships from empirical data. This is very important to realize. We use an objective technique to infer physically meaningful relationships from empirical data.
So basically, we had no end in mind. In other words, we had no theory in mind. We didn't
know what exactly.
No predetermined idea about what you were going to have.
Idea. And this non-dimensional analysis that Dr. Nikolov is talking about, it's known as the Buckingham Pi theorem. Basically, it directs you in how to create these non-dimensional numbers, which helps you to look at the data and compare one set of data against another set of data without getting the dimensions in the way, like measuring in terms of Kelvin or measuring in terms of watts or whatever. And that's what we do. So basically, you get these non-dimensional numbers, and you throw them in a basket, and you mix them around. In our case, we always mix our non-dimensional temperature that came out was a ratio of the surface temperature of any given planet divided by the temperature that planet would have or moon would have if it did not have an atmosphere. So we use both. In all cases, we use the measured surface temperature divided by either the emission temperature that we were talking about, that's the flat disk analysis, or the no atmosphere equation that we calculated. Okay, so basically, in this basket, we throw all these numbers, and we do regression analysis, and all the other terms had the rest of the measurements that were made by NASA on these various planets. Pressure, we would calculate density, or we would take it if it was measured.
So without going in any further details, because we really don't have the time to discuss this in detail, this is all in our papers, and people can go on the web actually and download our papers. They are free access papers, and you can read them. But the bottom line was that we discovered this interplanetary relationship, which is between the thermal effect of the atmosphere, which is measured by this ratio, temperature ratio of current surface temperature of the planet to the temperature without atmosphere. It quantifies the thermal effect of the atmosphere of any planetary body. We found that this thermal effect is entirely described and explained in a function of pressure alone, total atmospheric pressure, regardless of what the composition is. This was a measure, the first time we saw this, we could not actually believe our own eyes, because here we have those 6 bodies that have extremely diverse atmospheres. You know, you go from an amount of greenhouse gases of 0 on the moon to over 96% on Venus, and everything in between. And yet our analysis did not reveal any meaningful or any for that matter any correlation between the temperature and the composition of the amount of greenhouse gases, either in concentrations or partial pressure or whatever. The only relationship that was revealed, and it was extremely accurate actually, was between atmospheric pressure and this thermal effect of the atmosphere, which is this ratio of 2 temperatures that I mentioned. So basically the bottom line is that the long-term average temperature on any planet, we were able to predict using only 2 forces or 2 drivers: atmospheric pressure and distance from the sun or radiation reaching the top of the atmosphere of this planet. Our analysis showed that you don't need anything other than that to describe the 30-year long-term average temperature of any planet, and those are planets that are spanning pretty much the entire breadth of the solar system.
Mm-hmm. I should let me clarify the thermal effect that Dr. Nikolov is talking about is the temperature ratio, which for the Earth is basically the average temperature of the Earth is around a little over 14 degrees centigrade, which is 288 degrees Kelvin, and the no atmosphere temperature of the Earth is about 197. Well, if you divide that, you come up with a number 146. 1.46. That's the ratio. And what that means is that what the Earth does, the Earth's atmosphere does, is it accounts for 46% of the thermal effect that we see here on Earth due to our atmosphere. Now,
basically, the atmosphere increases the temperature on the Earth by 46%.
46%. So here at the distance that we have, here at our Earth orbit, basically that gives us the 288 degrees. If we were to move Earth out to the orbit of, say, Saturn, we would have the same, the ratio, 1.46, the 46% would stay the same. However, the amount of energy we would receive from the sun would be a lot less, and it would be a lot closer to what we see on Titan. Titan happens to have an atmosphere that's a little bit denser than the Earth. But this ratio is an important measure of the so-called greenhouse effect, or the warming ability of the atmosphere. And no one has used this ratio before to actually define the atmosphere. So one of the big results or findings of our discovery is to use this ratio to define the greenhouse effect, rather than this business of subtracting. Dr. Nikolov was saying that right now they subtract the temperature, the average temperature from the emission temperature, which is 33 degrees. Mm-hmm. In our paper, we discussed that this should really be 90 degrees. Well, these numbers are less meaningful. The number that really gives you what you need is to divide the measured average global temperature by the temperature it would have without an atmosphere. So for the Earth, 1.46, 46%.
So in other words,
so now let me interrupt here very briefly. What we are saying then is that the typical thoughts that greenhouse effect, CO2, carbon dioxide, and the water vapor are the controlling factors. Our so-called greenhouse gases are the controlling factors of our physical temperature on Earth, and in fact they have virtually nothing to do with it, according to this new theory.
There's a law called Dalton's law that we all learn in high school. That's the law of partial pressures. So basically, yes, CO2 does have an effect. It has a 0.04% effect. So each molecule holds its own according to its contribution to the heating that we get in our atmosphere.
So the heating is due, the thermal effect of the atmosphere is due to pressure. So individual gases, they have a contribution as much as they have contribution to the overall pressure.
To the partial pressure. Yeah.
So the partial so the effect of the individual gases is through their partial pressure. It's not through their concentration. It's not through the radiative fluxes that the current theory says it is. It's just a contribution, simple contribution to the overall pressure through their partial pressures. So carbon dioxide happen to have, in terms of volume, it's only a 0.04%. In terms of mass, it's 0.06% because it's a little bit heavier than the average air. But that's what the contribution of the carbon dioxide is to the overall, and really it's, in terms of temperature increase or temperature enhancement on the surface, is basically immeasurable. Because in order to change the temperature on Earth, say they're talking about now about 2 degree change in temperature of the Earth, right? To change the temperature of the Earth by 2 degrees, increase it by 2 degrees, create a warming in the order of 2 degrees, according to our empirical equation that is based on real data and explains accurately the temperature of all these planets throughout the solar system, you need to increase the pressure on Earth by 12% in order to get a 2 degree increase in global temperature. Mm-hmm. And 12%, think about that over every square meter of surface on the Earth, you have about 10 metric tons of air above your head. So a 12% increase, it means about
1.2 tons. Mm-hmm.
It's a ton, 1.2 tons basically of air has to be added over every square meter of surface. And that's enormous amount of gas, which we don't have any capability of producing, like technologically, and carbon dioxide that we're emitting in the air is just minuscule. It's basically its effect on the temperature through the pressure, which is the only effect you can have of the atmosphere, is immeasurable. It's minuscule.
Well, I know this gets into an area that's outside of your purview. I doubt that you want to even discuss it, but the bottom line is that this does put so much of the so-called greenhouse gas theory and the IPCC and Al Gore's calls for a $15 trillion financial input and a total change of our lifestyles on Earth to something completely different than we have today, this pretty much throws that whole thing right on its head if, in fact, your discovery is correct. Am I right in that?
Yes, you are.
Is absolutely correct.
And you know that $15 million and actually the amount, or 15 trillion, the amount of money that's being spent today on trying to scrub carbon dioxide, or the amount of time put into political arguments, or the business of carbon trading, all that money could be better spent on both climate research, and climate research that's not just specifically focused on climate warming, but on both climate research and on, frankly, on our environment, on getting to the real problems of air pollution.
Absolutely, because I recognize that both of you gentlemen are very solidly on the side of conservation and good, sound environmentalism, and I am the same way. Frankly, I'm very concerned about some of the things that we're doing to our planet, but that is something totally different. That's something that we should be dealing with, and in fact, the developed countries, the countries like the United States that have a profit motive in doing things, are doing a much better job than the countries around the world that have controlled economies and frankly don't have that profit motive, and they're not doing a very effective job. And I use certainly the Communist China as a perfect example of how they're really abusing the environment, and yet the environmental community doesn't seem to say a whole lot about that.
Yeah, Chinese have been actually excused and other developing countries from restricting their carbon emissions for the time being, and they fully support that because that actually allows them to go ahead economically while the Western world is being stifled. I mean, that's excellent for them, right? They're eliminating the competition. But let me mention something very critical here, important, so that the listeners can understand the difference that we're talking about. So you mentioned about Al Gore and all these efforts, to reduce carbon emissions and so forth. All these efforts, they have their roots, their fundamental arguments in the understanding of the nature of the greenhouse effect. And the current understanding that is in the mainstream, our research have shown that is fundamentally wrong. That the greenhouse effect is not a radiative phenomenon. The greenhouse effect is a thermodynamic pressure-controlled phenomenon. So if the background thermal effect of the atmosphere is due to pressure, therefore, you could not expect to have any change in the climate by changing a little bit, and we're talking really a tiny little bit, the composition of the atmosphere through more or less carbon emissions. It's just, in principle, not possible. And here's the interesting part. Pressure, this is for the benefit of the listeners, the definition of pressure, this is the physical definition of pressure, is basically a force per unit area. Now, force is something, so how the atmosphere creates pressure on Earth? It creates pressure because of its weight. In other words, it's a combination of the mass of the atmosphere times the gravity. So if you have the same amount of mass but you have less gravity or more gravity, you have less pressure or more pressure. So the pressure will change along with the gravity. So basically the efforts to try to stop, slow down, or prevent, or whatever the word is, climate change by trying to reduce or restrict carbon emissions is, from our new understanding of what the thermal effect of the atmosphere is caused by, which is caused by pressure and therefore by gravity indirectly, all these efforts means that you are trying, the equivalent to trying to alter Earth's gravity, to fight Earth's gravity.
Right.
That's the meaning of it, and how insane this notion is.
Absolutely. That was the point that this whole hour has really led to, is that last statement that you made, Dr. Nikolov, that the entire thinking behind this whole thing is absolutely absurd because it does not deal with the reality of what creates the Earth's atmosphere, the Earth's temperature, which is gravitational and things that we have no control over.
Exactly. Now, in this context, let me put something very important, because a lot of listeners will ask this question. Probably we haven't touched on this yet. It is that over the recent decades, and actually starting since the instrumental record exists in the 1880s or so until present, we have had some amount of warming. It's a mild warming. Actually, this warming began back in the 1600s when we started getting out of the so-called Little Ice Age. It's part of a natural cycle, but the total warming since the 1600s to the present, it's about 1.2 degrees Celsius. Between 1880, since we have thermometers available, and the present, the total warming is in the order of 0.8 degrees Celsius. So it's really basically over the industrial time, or since the Industrial Revolution, we're talking about in the order of 1 degree or less than 1 degree Celsius of warming. Now, this is undeniable, and people, when they say, "Are you denying climate change? Are you denying warming?" Nobody is denying that. The question is, what has been the cause for that? The recent satellite data that we have available since 1979, since the first satellites were put in orbit and they started measuring the Earth from above, until the present, the data are showing that there has been a slight reduction in the amount of cloud cover over the globe. When you have less clouds, you allow more solar radiation to reach the surface, therefore you have warming. And this has been shown to be the case both from satellite observations and surface observations. On the surface, solar radiation has been measured continuously on many locations. From the satellites, we have the measurements, of the cloud cover and the reflectance of solar light by the clouds. Both those measurements, they actually get to the same conclusion that we have a reduction of the total amount of cloud cover for a period of over 30 years, and the amount of increased solar radiation that this reduction brings to the surface is in the order of 2.7 watts per square meter globally, averaged. And this amount of increased solar radiation on the surface is more than enough to explain the observed warming or the observed increase of global temperature over the last 35 years. So the mechanism that controls the global temperature on a decadal time scale is very different from what we have discussed so far. The overall thermal effect of the atmosphere is due to pressure, but within this envelope that pressure and solar radiation creates in terms of energy envelope, there is slight variations of the climate possible, and those are possible because the solar magnetic activity affects the cloud cover directly and indirectly, and there is a lot of research done in this area, and the research has started about 20 years ago. And right now there is a kind of a agreed on hypothesis or theory that the sun affects the cloud cover indirectly through the so-called galactic cosmic rays. When you have higher solar magnetic activity, it shields the Earth against the galactic cosmic ray flux. And these galactic rays, when they reach the lower part of the atmosphere, they ionize the atmospheric molecules and the gas molecules, and they create those aerosols that serve as seeds to create the nucleus for clouds. So more cosmic rays basically increase the amount of clouds, and therefore they reduce the amount of radiation reaching the surface. And vice versa, when you have less cosmic rays, the amount of clouds is reduced. So basically, the sun, when you have more active sun, it shields the Earth from the cosmic rays, and you have less amount of clouds. So therefore, you have warming. When you have less active sun, there's more clouds because there is more of cosmic rays, and therefore it becomes cooler. So this is an entirely different mechanism that is responsible for the mild fluctuations of temperature if the pressure is constant. When the pressure is constant, if the pressure is constant on time scales of centuries, decades to centuries, the pressure is constant or nearly constant, then those little fluctuations are due entirely to the effect of the sun on the cloud cover. This effect has been responsible for the recent observed warming and has nothing to do with carbon dioxide or any so-called greenhouse gases.
Right.
Yeah, and I wanted to add, Dr. Nikolov was talking about the envelope. We haven't really pointed out that we're talking about a global climate, global temperatures. That's separate from the regional temperatures, regional climate. Mm-hmm. What I wanted to say is, for the listeners who are climate scientists themselves or very knowledgeable about some specific climate phenomena, our theory actually is a basket that you can put all the theories in. It doesn't negate any of the theories because we're looking at the long-term equilibrium. So when you're talking about ocean currents, you're talking about the glacial melting, the glacial freezing, nighttime, daytime temperatures. We have people that challenge us because we can't calculate the nighttime temperature in Fort Collins, for crying out loud. But our theory does not negate any of those theories. Radiative theory fits inside of the overall envelope, basket, I call it, of our theory. And part of the research.
So here is the key point to remember. So basically, we're not denying the existence of radiative transfer in the atmosphere. We're not denying the measurements that have shown that there is more radiation coming down than actually is absorbed from the sun.
Right. Right.
And
those are actual measurements. We're just have a different explanation for those measurements. So our theory basically does not put anybody out of business. It should actually enhance their research and improve their research.
Unless you happen to be predisposed to the idea that man is destroying the environment through the use of burning of fossil fuels, and therefore any, let's say, development, industrial development is a negative thing. If you believe that, which is really kind of the basis of some of this nonsense, then all of a sudden your theories are in direct contradiction.
Well, if you're a real researcher, that's a bias, so you need to start out without a bias like that. Yeah.
Absolutely. Well, that was kind of my point, gentlemen.
So basically, to summarize,
we've gone well beyond our normal program time here. So I have to say that we do need to end the show at this point. But I do thank you, gentlemen, for being part of this tremendous discussion. I know that there was a lot of science here for our listeners. I know that probably some of our listeners dialed out some of the scientific theories early in the discussion, but the bottom line is this whole new discovery that these gentlemen have made, as Dr. Zeller says, it doesn't contradict much of the science that's out there. It enhances it, and if we have true scientists that are listening to this and are interested, this should be a challenge to them to never say, as Al Gore has said, that the science is settled. There's no such thing. Science is continually being tested and retested to make sure that those theories are correct. And the only way we will ever do that is if we continue to think like scientists, and obviously Dr. Nikolov and Dr. Zeller, both of you gentlemen, think like scientists. So with that said, I will turn the radio show back over to Kelby, and I thank our listeners for joining us again this week in Connecting the Dots with Dan Happel, and ask that you return next week for a new program. Thank you and good night.
Ladies and gentlemen, that concludes this week's show with Connecting the Dots with Dan Happel. God bless. Good night. We'll see you next Thursday, 6 p.m. Pacific.